Euler's method. Objectives. By the end of this lesson, you should be able to use Euler's method to approximate a value on a particular solution curve given a differential equation and an initial condition. Before we begin, let's talk about what we can do so far given a differential equation of the form dy dx equals f of x comma y. So in other words, we're given a derivative that might have x's and y's in it. So far, we can draw the corresponding slope field. We can find the general solution if it's a separable differential equation. So we can find the general solution with a plus c. We can find the particular solution with no plus c if we're given an initial condition, again, if it's a separable differential equation. And with a differential equation, we can find an equation of a tangent line as long as we're given a coordinate point, so an x and a y. So what Euler's method is going to add to this is it's going to allow us to numerically approximate values on a particular solution curve given a differential equation with an initial condition. And it's going to involve using tangent line approximations that hug the solution curve. So we're going to need to be given a differential equation and an initial condition, and we're going to approximate other values on that particular solution. Let's start by considering this differential equation dy dx equals 1 plus y with this initial condition y of 0 equals 1. So I'm going to stop right there. We've been given a differential equation, so I can plot its slope field, which is this image off to the left. If it's separable, I can find a general solution, and it is separable. I can divide by the 1 plus y, so dy over 1 plus y, and then multiply by the dx differential. So I can separate the y's from the x's, I can integrate, I can find a general solution, and because I'm given an initial condition of y of 0 equals 1, I can find a particular solution that passes through this point. So now let's see what the problem is asking us. We're being asked to approximate y of 3 without solving the differential equation. So approximate y of 3, meaning there's a specific value for y of 3. And I want to clarify that I can find y of 3 exactly, because solving this differential equation would give me y equals some f of x, which of course I could just substitute 3 in and find y of 3 exactly. But the point is, I want to approximate y of 3 without actually going through the process of solving the differential equation. And in a lot of the cases we're going to look at, we're not going to be able to separate the variables, so these are not even, it's not even going to be an option to find the answer exactly. In this one it is, but in general it might not be. So we want to approximate y of 3. So let's think about what we can do. So we said we can draw its slope field, perfect. We want to consider the particular solution that goes through 0, 1. So because this is a slope field, if I want to pass through 0, 1, this image on the right is a sketch of what the particular solution curve is going to look like that goes through 0, 1. So this curve is y equals f of x. And if I'm being asked to approximate y of 3, well, 3 on the x-axis is right here, so I want to approximate the function value that's way up here on this curve. So this curve goes up and up and up and up, so I'm trying to find f of 3. So we'll say that it's right there. It's a little off center, but that's the value we're trying to approximate without actually solving this differential equation. Alright, so one of the other things we said we could do, given a differential equation and a point on the graph, is find an equation of a tangent line. So we do have a point. This is the point 0, 1. So I can find the equation of a tangent line right at 0, 1 to this particular curve. So I can find the equation of this line right here. So I can find the equation of this tangent line. Now, if I used this tangent line as a linear approximation, I'm not going to get a very good answer. So if I could see this line continues, if I try to figure out what the approximation is, if I substitute 3 into this line, notice how far off I am from the actual y value that's the solution. So it's not a very good approximation. So what we want to do is use Euler's method to create sort of a series of line segments that are going to hug the curve. And this first linear approximation is going to be the first line that we consider. Alright, so we saw a generalization of what we're trying to do, so now let's get a little more specific with this example. So we can create a tangent line at 0, 1, and the specific slope is going to be found by substituting 0, 1 into dy dx. So dy dx at 0, 1 equals 2. So off to the corner I'm going to write down what dy dx was just as a reminder. So dy dx was 1 plus y. So substituting 1 into this y value, 1 plus 1 is 2. So here's my slope and here's my point. So that means that this first tangent line that passes through 0, 1 has an equation given by y minus 1, so I'm using this coordinate point, equals 2, the slope, times x minus 0. So here I can just go ahead and add the 1 over, so y equals 2x plus 1 is my first tangent line. So y equals 2x plus 1 is the tangent line that goes through 0, 1, and we're only going to consider it between x values of 0 and 1. So now I can figure out what coordinate point my tangent line goes through at 1. So at 1, this coordinate point passes through 1, 3. So I can substitute 1 into this tangent line. So y of 1, so 2 times 1 plus 1 equals 3, which if we drew it carefully we can see on the graph. So in other words, I have a coordinate point, another one, 1, 3. So if I want to create another tangent line, I'm going to need another slope. So to find the slope, I'm going to go back to my original differential equation. But now I'm going to use this coordinate point on my first tangent line approximation. So here's my coordinate point. My slope that's going to correspond to 1, 3. So dy dx corresponding to 1, 3 now is going to be 1 plus 3. So my slope here is going to be 4. So if I wanted to write the equation of this new tangent line, I'm going to have y minus 3 equals 4 times the quantity x minus 1. So here I have 4x minus 4, and then I'll add the 3 to the other side. So I have 4x minus 1. So this is now the equation of this second tangent line that now we can sort of see hugs the curve more than if I were to have just continued on with the original tangent line approximation. So this green line segment here comes from the line 4x minus 1, but we're only considering it between 1 and 2. So we can continue this process. We've gone from 0 to 1, now 1 to 2, so we can continue this process from 2 to 3. So we can use this coordinate point up here at 7. So 2, 7 is going to be our next coordinate point. And again, to find our slope, we're going to use our original dy dx over here. So this process, the way that I've written it, has gotten a little bit lengthy. So what we're going to do is now just come up with a concise way of doing this. And we arbitrarily chose to use a distance of 1 unit. So we chose the next coordinate point 1 unit away from 0 and then 1 unit away from 1. But we're going to be able to choose any distance we want, and the smaller distance we choose, the better we're going to hug this original solution curve. Before we formalize the process, here's one graphical example of a solution curve and then us creating a sequence of tangent lines that in this example are closer together than the previous example. So in the last one we went from 0 to 1, and that every distance apart between our tangent lines was a unit of 1, but now we can see that if we make that distance smaller, then we're going to hug the curve even closer. So we're going to have a better and better approximation for a value specifically on the solution curve without actually finding the equation for the solution curve. Moving on to another example, we're given dy dx is x minus 2 with initial condition y of 0 equals 5. Part A says we want to find an approximation for y of 0.8 using Euler's method with two equal steps. So we weren't told exactly what our step size should be. We have to figure it out based on the fact that we are starting at an x value of 0 and we need to get to 0.8 using two equal step sizes. So in order to get to 0.8, we're going to have to go up by 0.4 once and then go up by 0.4 again to get to 0.8. So my step size is going to be 0.4 every time. Now filling out the table, the first row is going to be the same, and our first x and y old value come from the initial condition, so 0, 5. And my dy dx, I will go ahead and fill in that formula, that's x minus 2, so that should be included as well in that first row. Now substituting in my x value here into dy dx, my x value was 0, so 0 minus 2 gives me a slope of negative 2. And then I'm taking 5 and I'm adding it to 0.4 times negative 2 to get my y new value, which is 4.2. So 4.2 is now going to become my y old in the next row, so 4.2 gets substituted in. And now to find my dy dx, that's only dependent on the x value, so I'm going to have 0.4 minus 2. So I'm going to have negative 1.6 as my slope. So to find my y new, I'm going to add 4.2 plus 0.4 times negative 1.6, which is 3.56. And then the final one is, my final y old is the 3.56. So there's a part B to this problem. Now we're going to solve the differential equation, dy dx equals x minus 2 with initial condition y of 0 equals 5, and then we're going to calculate y of 0.8 exactly. So we can do this because this is a separable differential equation, so we have dy dx equals x minus 2, so dy equals x minus 2 dx, and we can integrate both sides. On the left we're going to have our y, on the right we have x squared over 2 minus 2x plus c, and our initial condition is y of 0 equals 5, so y of 0 equals 0 squared over 2 minus 2 times 0 plus c has to equal 5, so in other words c is 5, so I will just go ahead and bring that over here. My equation, my solution with this initial condition is y equals x squared over 2 minus 2x plus 5. So this is the exact solution. So if I want y of 0.8, I can substitute 0.8 into my x values. So I'm going to have 0.8 squared over 2 minus 2 times 0.8 plus 5, which equals 3.72. So y of 0.8 is exactly 3.72, and using our two-step Euler's method approximation, we said y of 0.8 was approximately 3.08. So that's not too far off for using Euler's method with 0.4 as my step size and only using two approximations as opposed to solving the differential equation. But again, you might be thinking, well, this wasn't too bad to solve and just substitute in, but some of our differential equations are not solvable, as in they're not separable, and we don't have the strategy to do so. So to find approximations on the exact solution curve, we need to use Euler's method. Let's look at another Euler's method problem where information is given to us in a different format. So assume f and f prime have values in the table. Use Euler's method with two equal step sizes to approximate f of 2.6. So we were used to y and dy dx, but now we're given f of x, so y equals f of x, and f prime. So that corresponds to the dy dx that we were used to. But we're given the same information here. It's just in tabular form. So at different x values, 3, 2.8, 2.6, we know f prime of x, or dy dx, are 0.4, 0.7, and 0.9 respectively. And we know that at x equals 3, f of x, the function, is 1. So there's my initial condition. When I plug in 3 into y, I get out 1. So when I create my table, this bottom table is now the one I would create to use Euler's method in a systematic way. My initial condition, my coordinate point, is 3, 1. And my delta x is going to be negative 0.2. So we're starting out at an x value of 3, and we need to get to 2.6. So in the previous examples, we were building up to that coordinate point, but now we want to go down to 2.6, so that means we're going to need to have a negative step size. So to get from 3 to 2.8, I'm going to need to go negative 0.2. So negative 0.2 is my delta x every time. And now my dy dx is really my f prime of x at these different x values. So f prime of x, well, the x value is 3, so f prime of x at 3 is 0.4. So 0.4 is going to be my slope, and I'm still performing the same operation across here. It's 1 plus negative 0.2 times 0.4, and that is 0.92. And now 0.92 can move down to my y old. And again, I'm still going to add my delta x, my negative 0.2. And this time I need f prime of x, where my x value is 2.8. So at 2.8, f prime of x is 0.7. And if I perform the operations in the second row, I'm going to get 0.78. And then finally, I'm going to have 0.78 plus negative 0.2 times my final slope, which is f prime of 2.6. So that is 0.9. And performing the last set of operations, I'm going to end up with 0.6. So 6/10 is the approximation for f of 2.6. So f of 2.6 is approximately 0.6. Alright, let's look at a final example. We want to let dy dx equals 2x minus y. If y equals 3 when x equals 2, use Euler's method with 5 equal steps to approximate y when x equals 1.5. So what I want to do on this last problem is really just focus on how to set up this table and really just making sure that we pay attention to details, because after that it's all just a lot of computation and arithmetic. So we have to know what is in this initial row. So it's always the same: x and y old, delta x, our step size, dy dx, so I'm going to fill in my specific dy dx, and that is 2x minus y, and then my y new equals y old plus my slope times my change in x. So we need to start out by filling out this initial row. And I would also advise putting in the actual formula for dy dx, so 2x minus y. And on this problem, I want you to pay attention to the fact that this is not a separable differential equation. So we actually cannot find a specific solution, even though we have an initial condition. We don't have a strategy for solving non-separable differential equations here. So now the next thing we can go ahead and fill in is our initial condition. So if y equals 3 when x equals 2, then our coordinate point is 2, 3. So my starting x is 2, my starting y old is 3. And we want to use Euler's method with 5 equal steps to approximate y when the x value is now 1.5. So if we started at x equals 2 and we need to get to 1.5, with 5 equal steps, I'm going to go down by 1/10 every time. So we can fill in both the x and delta x column, because x is going down by 1/10 every time. So 2 goes to 1.9, 1.8, 1.7, 1.6, 1.5. So that means my delta x is negative 0.1 every time. And so at that point, that's when we start going through the motions of filling out the rest of the chart, moving across row by row. Now this 1 is a nice whole number to begin with for my initial slope, but we'll do one row together to see that in this particular example, they don't end up as nice whole numbers or even nice numbers to necessarily figure out by hand, or that you'd want to, because our slope is now dependent on x and y. So in the previous examples, the slope dy dx was only dependent upon x or y. So now that there's an x and y in my dy dx, it's just going to be an extra computation along this dy dx column. So 1 was obtained from multiplying 2 times 2 minus 3. So substituting in the 2 for x, this is 2 times 2 minus 3, and that's where the 1 came from. So now, to find my y new, it's going to be 3 plus negative 1/10, and then that's times 1. So that's, again, a nice whole number that we started out with. So this is really just 3 plus negative 1/10, so 2.9. So 2.9 is now my y old for the next row. And let's just go ahead and find dy dx together here. So it's just it's an extra computation that we have to perform. So now we have to do 2 times my x value on the second row is 1.9, and then minus 2.9. So not that this is that difficult, but just another tedious computation. So in that case, I'm going to get 0.9 as my slope, and then I'd have to do 2.9 plus negative 0.1 and then times 0.9, and that will give me 2.81 for my next value. So you can see that now, in order to find my dy dx, it's just going to be a little bit uglier of numbers every single time. So we can, of course, finish this chart off, but the point of this is just to ensure that you know how to set up this table and work your way through it. So just be really careful about the arithmetic and the computations, even though you're using your calculator, because if you mess up in the first step, second step, any of the steps before the final answer, which would be this one here, you're going to end up with the wrong answer. So you just have to be really careful, especially when you're asked to do this many steps using Euler's method.